Recommendation systems are present in a lot of different fields, but for someone with no prior knowledge, the outputs can feel untrustworthy and random. That's where explainable recommendations come into play. In this presentation, we will start off by giving you the what and why of explainable recommendations. Then we will show you two ways to classify them. We follow that up with some explanation on how they work regarding the information source and the display method. And then lastly, we showed two different ways to get explainable recommendations using both a model intrinsic and a model agnostic approach. A recommendation system takes input data and traditionally uses either content-based filtering or collaborative filtering to generate recommendations for the users. Content-based filtering uses the similarity of an item to other items that are already connected to you in some way. Collaborative filtering is when the system compares you to other users and recommends items that were chosen by similar users.
Most AI systems nowadays use complex black box calculations to transform the given input into a certain output. Because we don't really know what happens in this black box, the system cannot give an explanation for the decisions that it makes. With explainable AI, we try to step away from the black box system and hold the artificial intelligence accountable for the output that it gives. This way, errors and biases can be detected more easily. Instead of just giving a recommendation based on given input data like a normal recommender would do, an explainable recommender also gives an explanation to why a certain recommendation is given. Recommendation systems are all around us. Facebook uses it to give you suggested friends. Netflix and Spotify use it to recommend new content. When looking for a nice place to stay, Booking.com recommends places based on your last visits, and Amazon tries to suggest items you might be interested in buying. An explanation is a piece of information displayed to users explaining why a particular item is recommended. The explanation can be generated from different information sources and can be presented in different display styles. The display style could be textual, visual, or social. A few examples of information sources are user-based or item-based sources and feature-based and social-based sources. The models used to train and generate the recommendations can be categorized to intrinsic models and agnostic models. We will explain these two later on. Now we discuss some of these information sources in more detail. The traditional way is user item-based explanation. For example, if you get recommended a lens for a camera in a user-based system, it is recommended because a similar user to you bought this lens before. In an item-based system, you get recommended a lens because you recently bought a camera. In feature-based recommender systems, features are defined and applied to the items and to the users. The user gets recommended the item that overlaps the most with their features. In the example below, item 1 would get recommended to the user because it lies closest to the graph of because the user lies closest to item 1. Opinion-based information sources are sources that use machine learning to detect which aspect of an item is most relevant in the opinion of other users and makes recommendations based on that. There are also different methods of displaying the generated explanation. We discussed 3 of them. The first method is sentence explanation. Like it says in the name, it gives a sentence explaining why a certain recommendation is made. Another method is visual explanation. This method uses pictures and other visuals to intuitively explain the recommendation. The last method we discussed is a social explanation. This could be used in social networks to explain why a certain person is a suggested friend.
When deciding on an explainable model, you can follow two different philosophies. On the one hand, you have the model intrinsic approach. Here, the models you choose are inherently understandable and you automatically generate an explanation alongside the recommendation. On the other side, we have the model agnostic approach. Here you get to choose whichever model you want and you do post hoc analysis on the result to generate the explanation. Let's dive a bit deeper into these two approaches by giving some examples. Some intrinsic model options are the following: decision trees, deep k-nearest neighbors, self-explaining neural networks, knowledge graph-based models, and the rule mining model. These are all inherently understandable because of the underlying structure. Now let's take a look at those last two in a bit more detail. First are the knowledge graph-based models. Knowledge graphs contain rich information on entities and relations. It is structured in an SPO format, that is subject, predicate, and object. Many typical search engines will use a similar system. Here recommendations are based on pathfinding algorithms on this graph. Because the backbone is a graph, it is automatically visually clear where the recommendations come from, so it's human readable. Secondly, we have the rule mining models. The recommender system will try to learn rules about the items it can recommend. If two users, for example, watch movie X and then user 1 watches movie A immediately after, the recommender will add the rule after X recommend A, and movie A will then be recommended to user 2. The handy thing with this model is that the so-called rules can be easily adjusted by user feedback. The system gets smarter or more correct with more feedback and more users. Then lastly, we take a look at the other approach, the agnostic models. Like we said before, with this approach we are not limited in our choice of model. This time we will generate an explanation after the black box recommender system has made the recommendation. This is often done by approximating model behavior using a simpler interpretable model like, for example, LIME. This stands for Local Interpretable Model Agnostic Explanations, and this can explain individual predictions. Let's look at this example where we have a system that predicts if an image is a frog. We split up the image in some way to interpretable components. Then we leave out certain parts of the image and do the prediction again. This is called perturbing the data around its neighbors. And finally, we then fit a regression function weighted by the proximity to the original sample. In the case of this image, we see that the head of the frog is the resulting explanation. We can take the same approach when analyzing a black box recommender system, where we can, for example, find out which part of a movie description led to recommending a similar movie. We hope that we've convinced you that explainable recommender systems will have an important role in the future as AI becomes a bigger and bigger part of our world. You now have some basic knowledge of different approaches that can be taken and how these systems might be implemented.